Good morning and welcome back. Part J deals with the transfer of heat. There are a number of different methods by which thermal energy, heat in other words, moves from one location to another. I've listed three of the ways. First, there's infrared radiation, and then there's conduction, convection. We will discuss those methods in order, beginning with heat transfer. After we've discussed heat transfer, and that won't occur in this first lesson, we will also discuss the concept of humidity, but that's for later. For now, we'll just look at heat transfer by infrared, or we can say IR, radiation. I show an object that's radiating infrared. You learned in an earlier part of this course that infrared radiation, as well as visible light and other forms of radiation, are all of a type called electromagnetic radiation, which carries energy away from objects in the form of waves, electromagnetic waves. What we will be interested in doing is calculating the number of joules of energy, IR energy, radiated away from an object each second. Energy per second, joules per second to the units, but you may recall that a joule per second is also a watt quantity. And so we will be reporting our answers for the question, how much energy is radiated away each second in units of watts, abbreviated W. I show here an object at a certain Kelvin temperature, symbolized as T. In the past, we might have symbolized the Kelvin temperature with a subscript K, but we won't in this discussion. The object under question has a surface area symbolized as A, and the units, of course, will be standard units, square meters. Every surface has a property called its emissivity. It's a dimensionless quantity, a unitless quantity, and we symbolize it as E, emissivity. There is a quantity in nature that relates to the emission of infrared radiation. It's called Stefan's constant, and we symbolize it using the Greek letter sigma, which is lowercase s, first letter of the last name of this gentleman. Stefan is his last name, not his first. And it's a pretty ugly looking number. As is always the case, you don't need to memorize any of these constants. They all will appear on the equation sheet that you will use on examinations. So finally we come to what I call the rate equation. R stands for the rate at which energy is emitted, rate being a rate or quantity per time, joules per time, energy per time, joules per second. R is the symbol that we use. And there is the equation. Sigma EA times T, the Kelvin temperature, raised to the fourth power. I'll work a problem involving specific numbers. We'll have a sphere, suppose, whose radius is given as 1/10 of a meter. And suppose its emissivity is 0.30. And it's a unitless quantity, as I think I've already said. Suppose the surface temperature is 300 degrees Kelvin. In order to find the rate at which energy is emitted from the sphere, we need to know the area, the surface area of the sphere. Well, the area of a sphere is calculated using the equation 4 pi r squared. Not an equation you need to memorize. Again, it'll be on the equation sheet. Well, we calculate the surface area first, 4 pi times 0.10 squared, and I got 0.13 square meters. Now we're ready to go. Substituting for sigma, E, A, and T, we have this expression. Sigma, then E, then A, then T raised to the fourth power. The final answer is 17.9 watts. Now, what I would urge you to do is to verify that the units will properly cancel, leaving behind the only surviving unit. W stands for watt. So on your own, please substitute in the known units for Stefan constant, shown here, that ugly collection, watt per meter squared Kelvin fourth. Put it there, nothing there, square meters there, and that will be degree Kelvin and raised to the fourth power. Everything cancels except the W. Final answer again, 17.9 watts. It's important to get a sense of how much energy that is. The reading lamp that you might have on your desk at home is typically going to be 60 watts. 40 watts is pretty dim, and half of that, less than that, is what we're talking about here. That concludes our first discussion of the first topic in chapter or part J in Physics 17. There will be multiple more parts to come. Stay tuned, and also stay safe. Don't touch your face. Goodbye.